Hi, my name is John Bodner. Like Dave said, I'm a software engineer at Capital One in the Tech Fellows program. And today, I'd like to talk about Go's features. You know, when we geeks get together to compare our favorite programming languages, we always brag about the features. You know, my language, it has immutability, or my language, it has generics, or my language has unreadable syntax. So personally, I think one of the best features of Go is its lack of features. The creators of Go have focused on a simple syntax, good tooling, and readable code. And those things get you a pretty long way. So what I find interesting is stretching those features as far as I can, seeing what can be done with Go's limited feature set while keeping your code readable and maintainable, perhaps making it more readable and more maintainable. So the genesis for this talk was actually about a year ago. I was starting on a new project in Go with a coworker who was Go curious. He had dabbled in a few programs, but had never really used the language before in a big project. And we were discussing how to implement data access libraries in different languages. And I mentioned JDBI, which is the Java Database Access Library. And unlike some of the unfortunately better-known Java ORMs, JDBI actually tries to be simple. So you define an interface with the methods that you want, and annotate the methods with SQL queries that you want to run, and you put annotations on the method parameters to associate them with the query parameters. And so, for example, in the create something table method, there's no parameters, you're just going to run that SQL query and the SQL update annotation. Or for insert, you see the bind annotations on ID and name. They get associated with the ID and name parameters inside of the SQL and the SQL update. And the same is true for find by ID and find between. And then at runtime, you instantiate a handle object, and you pass a reference to your interface into the attached method on handle, and it spits out a working DAO. And after showing off JDBI to my coworker, I mentioned in passing that you could build this with Go, and he thought it was impossible. After all, Go doesn't have annotations or dynamic proxies, which are the two features in Java that let JDBI do its magic. But I'm stubborn. Once you tell me something's impossible, I'm going to find a way to actually make it work. So let's look at the requirements. In order to look like JDBI, we need to specify queries in line with the code. We have to generate the code to implement the queries. We have to ensure type safety. We got to prevent SQL injection attacks. And you got to make sure the performance is going to be reasonable. But there's actually one more overriding requirement. This needs to feel like Go. That means the solution should be composable with other Go code. You want a library, not a framework. It shouldn't replace the standard SQL libraries and patterns. It should just work with them. So I thought really hard. I tried a bunch of ideas, wrote some code, and here's the solution. It's called Proteus. So here's how you set up using Proteus. You define a variable, I have a person DAO variable of type person DAO, and then in the init method, I pass it off to this build function. And in main, I set up my database access, and I call do person stuff. And in do person stuff, you call create and get and update and delete. And actually, on my machine, I've got Postgres installed, the simple database. So let's run this code and watch it work. And let's make sure demos work correctly. All right, so we create a row in the database, and create a second row, and create a third row. We're going to do a get from the database and pull back the results. Do a get all, pull back all the results from the database we just created. We can use an in clause and get back 2 values, or get back 3 values from an in clause. We can do an update to the database, and we get the updated value back from the database. We do a delete from the database, and if we try to get our deleted record back, nothing comes back. So that's Proteus. Thank you very much. Any questions? All right, okay. All right, let me actually show. So how did I do that? Let's see how we can combine Go's features and to build something new. So in order to build Proteus, you have to start with reflection. Has anyone here used reflection in Go before? All right, good, a lot of you. So for anyone who hasn't, the tools are in the reflect package in the standard library, and they're not too hard to understand. So first of all, you get the type of a variable, the reflect.type, by calling the reflect type of function and passing in your variable. And once you know the type, you can get the kind. The kind's what the type is made out of. Slice, map, pointer, struct, array, interface, various primitive types. The difference between the kind and the type can be a little tricky to understand, but think of it this way. If you define a struct named foo, the kind is struct, the type is foo. And if your variable is a pointer or a map or a slice or a channel or an array, you can find out the underlying type by using var type.lm. and types of other methods on them help you find out the structure of the type of the variable, and we'll see some more of those as we go along. And finally, when working with reflection, it's sometimes useful to generate a type token. Usually you have to create or compare a type, but there's no instance around to start from. And this is a little bit ugly, I'll grant you, but it does work. And in addition to finding out the types of your variables, you can use reflection to read or set or create values. So first, you use the reflect.valueOf function to create a reflect.value from your variable. And if you want to use reflection to modify the value, you make it a pointer to the variable. Otherwise, you just call it directly, and then you can read the value. And once you have a reflect.value, you can round trip the value back to a regular Go variable by using the interface method. And if you use a pointer, you can call lm.interface first, and this will return back something of type empty interface. You have to cast it back to the real type underneath it. If you want to modify the value, remember, it has to be a pointer, so you have to dereference the pointer first, use lm.set to make the change, and you pass in of reflect.value to change the value. And finally, if you want to make a brand new value, you do it by calling the reflect.new function, and you pass in a reflect.type, and then you have a reflection value that you can then use to modify things. So there's lots of other stuff in the reflect package. This covers about 90% of the things you're actually going to do. We'll see a couple more things along the way. So let's figure out the other tools that we can use. We want the SQL queries to be visible, and JDBI uses Java's annotation support to do that. And if you're not familiar with Java, annotations are metadata that you can put on basically anything in a Java program, methods, parameters, classes, interfaces, and they're visible at runtime. There's one thing in Go that kind of sounds familiar, and that is struct tags. So they hold metadata about the fields in a struct, and they're visible at runtime using the reflection package. And if you've never played with it, here's a little bit of code that takes in an empty interface, makes sure it's a struct that was passed in, and then prints out the values for tag 1 and tag 2 on each field in the struct. And you see in the first line we call reflect.typeOf, and check the kind to make sure it really was a struct that was passed in. And then we use the num field method on the struct, on the type of the struct, to get the number of fields, and then we pull each field out, and we then get the name for that field and the tags for that field. So if you defined a struct that looks like this, and you ran some code, you get something out that looks a little bit like this. Not too bad. This is pretty straightforward. So that's another piece. We know how to store our queries. But now we need something that will actually run our queries. How do you at runtime look at a SQL string and make it into runnable code? Has anyone done things like this before in Go? So this is actually kind of neat. You can generate functions at runtime in Go using reflection. And let's see a generated function in action. Anyone here familiar with the idea of memoization? It's a fancy word for caching if you haven't heard of it before. So if you have an expensive calculation, you can compute it once and store the value and just return back that cache value over and over again. So let's define a type called calculator. That's a function that takes in 2 ints and returns back an int. And I've got some code here that implements memoization in Go for calculator. Not too hard to follow. You create a type to hold the parameters, a map to store the calculated values, and you pass a closure to the reflect.makeFunc function that checks that map for input parameters, and if the values aren't present, it runs the real function and caches the values in the map. And the next time you call it, it'll pull the values out of the cache. And you see that closure that's passed in to reflect.makeFunc, input parameters of type reflect.value, output parameters of type reflect.value, and you just convert back and forth to work with it. And so let's say we have these two functions, add slowly and add normally. Those are both of type calculator, so we can memoize them with our code. And let's run some benchmarks to see how long it takes for them to run with and without memoization. So there we go. All right. So the first one will take about a second. And memoize takes around 250 nanoseconds, give or take. Come on, there we go. All right, and add normally is like 0 times, it's a third of a nanosecond, and memoize add normally also around 250 nanoseconds. So if you're doing something that's really fast, like just adding two numbers together, generated functions and reflection are going to add tremendous overhead. It's not a good fit. But if you're doing something slower, like say talking to a database, the overhead is noise, not even going to measure up in what you're actually doing. So I think for the database case, we're not going to have bad performance using these generated functions. All right. So since we need to use struct tags to hold the metadata, we know that we need to use a struct as the frame to hold our generated SQL queries. So what you might not realize is that you can use function types for the fields in a struct. So you can define a struct as function fields, put struct tags on those function fields, and then at runtime, you pass an instance of the struct into a function that will populate the struct's fields with dynamically generated function implementations that implement SQL calls based on a query provided in the struct tag and the parameters for the function. And that's what we've done here. So we have our person DAO. That's what I was hiding before. This is a bare skeleton, but we'll keep filling it in as we add features. You declare a packageable variable of type person DAO, and in init, we're going to pass it into this build function. And after we call build, the functions will all be filled in, and we can use them in our code. So as an aside, this is not an interface. Even if you have a struct that fields the same names and types as methods on an interface, this struct will not implement that interface. So be aware of that. But when you use it, this is what the code looks like. It looks just like standard Go code, just calling the function fields you created on that struct. And we've already can start filling in what build looks like from everything I've talked about so far. Since there's no base type in Go that means a pointer to any struct, build takes in an instance of type empty interface, and an error is returned in case something goes wrong when building the implementation. And first, we can get the type of that DAO pointer that was passed in, and we make sure it's a pointer to a struct by using reflect.typeOf and checking the kind. And once we confirm that we have the right type, we use reflect.valueOf to get the reflect.value, and then use lm to hit the actual DAO behind the pointer that was passed in. And this is just like the example code for the struct tags before. We iterate over the fields in the struct, and we look for fields that are of type function, and they have a SQL query struct tag with the name proq. And when we find one, we call a function that will build an implementation, and then we assign the implementation that was returned to the DAO values field. And once you go through all the fields, we're done, and we return from build. And for now, as a placeholder for make implementation, we're just going to show that we can generate a function, just going to print out the query string to the console. And if you run the code I've shown so far, you get something like this, where you call create, you get the placeholder, and get, and update, and delete. And this is good. It shows that the basic concept works, but it doesn't do anything. So let's start making it actually do things. Let's make it run some database queries. The next step is figuring out how to integrate our library with the standard Go SQL libraries. We want to be part of the Go ecosystem, and we don't want to rewrite all the SQL libraries, so we're going to have to play nice. There are two main types in the Go standard SQL library. There's SQL-DB, that represents a database connection pool, and SQL-TX, which is a database transaction. If we're going to work with the standard SQL package, we have to be able to use these types from within Proteus. And queries in SQL in general can be broken down to two broad categories, those that read existing data and those that add or update or delete existing data. And the Go SQL libraries have the same two methods on SQL-DB and SQL-TX, one for reads and one for updates. The read method looks like this. It's called query, takes in a query string and some arguments, returns back SQL rows and an error. And for updates, it's called exec, takes in a SQL query and the parameters for the SQL query, returns a SQL result and an error. So in order for Proteus to integrate with the standard library, define two interfaces, query and executor that has a single method that matches the query and exec methods, and a wrapper that just composes query and executor together. And this rows thing as well. So for some reason, SQL.result is an interface, but SQL.rows is a struct. And I didn't want Proteus to depend on any concrete types, so I defined a rows interface as the same method as the SQL.rows. But doing that leads to a little quirk in Go's type system. The query method on DB and TX returns that SQL.rows struct, but Proteus is looking for this rows interface. And even though SQL.rows meets the interface of a rows interface, Go doesn't consider the interface met. If you tried compiling indirectly, it would fail. And so to work around this, I created a tiny adapter type that dispatches back the results and a function that wraps DB or TX in an adapter so that Proteus can work with it. It wasn't quite as seamless as I was hoping, but the value of rows being an interface far outweighs that one-line cost. And here are the definitions of the interfaces. We have querier, executor, and wrapper, just like I described. And here's the rows interface that takes the methods off of the SQL.rows struct. And here's the adapter codes. We have the adapt function. It returns back a wrapper and our SQL adapter type that is able to map things. And that SQL type that's mentioned there, there's an interface that's defined over here as well. And let's start looking inside of Proteus code to see how to actually build this out. So the build function doesn't change at all, so we can skip over that for now. The make implementation function now checks the first parameter of the function field that was passed in. And it dispatches to a different function generator depending on whether the first parameter is a querier or an executor. If there are no parameters, the first parameter type is wrong, error is returned. And we use the type token here because doing a standard Go type switch requires you to have an actual value. And at this point, we don't have any values, just types. So our implementations now return functions that convert the reflect.value to the correct type and call the database layer with the query string from the struct tag. And so for now, we'll sort of just print out the values returned from the database calls. We'll handle actually returning values back in a little bit. And you see here's the make executor implementation. We pull that first parameter out in our closure. It pulls out the executor. And then we just call executor.exec, pass in that query, and we print out the results that come back. And for queryers, make query implementations basically the same thing. We pull out the querier from the first parameter. We call query.query and pass in the query and print out the results. And now that we've done the insides, let's go back to our client code. And we put that first parameter in for our struct fields. It's an executor for create and update and delete, and it's a querier for the get function. And we'll put in our SQL queries here also. In real Go code, you have to put the struct tag in the same line as the struct field, but to fit on the slide, it's on the next line down. And you see the queries have placeholders in it. So we have like update person set name equals colon name, age equals colon age, ID equals colon ID. And those placeholders are nice for giving named fields. And we'll talk in a little bit how to get the values into those placeholders. And since we defined our query and executor, we're ready to start talking to the database. And so we'll initialize database connections in main, and we'll wrap it for access with Proteus, and we'll pass it to our doPersonStuff method. And when you run the code, and you can see we're talking to the database, but we're just getting back errors because those are not valid SQL queries. It's colon name, colon, age, colon, it's not actual database syntax. But for create, we get back an error, and get, and update, and delete, we get back errors. This is actually a good thing, though. We are talking to the database and getting the error back from the database. So the only problem is our placeholders aren't valid SQL. So let's do that next. Let's turn our placeholders into valid SQL prepared statements. What we need to do is associate the placeholders in SQL with the parameters on the function fields. And our function field for update, for example, is going to have an executor for the first parameter, and then ID and name and age as the function parameters that are on that field. And in the SQL query, you have colon name, age, colon, ID colon. So as we associate those function parameters with the SQL query's function parameters as well. There's two layers of difficulty with solving this. The first is that the names of the parameters for a function are not preserved at runtime, so you can't grab them using reflection. So if you want to use meaningful names, you need another way to specify those names. Solve this problem by adding a second struct tag key value pair with a key name prop and the value that consists of a comma-separated list of the parameter names in the order in which they appear in the function's parameter list. The query or executor, we can skip over that one. Don't really care about it in this case. So the second problem is that every database has its own syntax for the parameters in a prepared statement. MySQL and SQLite use a question mark. Postgres uses a $ and a number. Oracle is a colon and a number. And we need to be able to map to any of those. So we're going to define a new type called param adapter. It's a function that takes in a number and returns a string. And Proteus, out of the box, includes implementations for MySQL, Postgres, SQLite, and Oracle. You pass in, into the build function at runtime, you pass in the param adapter along with an instance of your DAO, and that will tell Proteus which syntax to build it for. And here's what param adapters look like. The type, like I said, is a function that takes in an int, returns a string, and implementations for the various databases. It's only a question mark all the time for MySQL and SQLite, and Postgres and Oracle have to take the position as well. And rather than look at all the code changes, let's go over the logic that we use to go from struct tags to SQL. We start with the proq and prop struct tags and their values. And then we convert the contents of that prop struct tag to a map from string to int. The key is the name of the parameter, and the value is the order of the parameter in the function. So you get ID, name, age is the value of prop. You get back a map where the key ID has a value 1, key name has a value 2, key age has a value 3. And this is the name order map. You then take the values of the proq struct tag and the name order map and the param adapter, and you generate two things: the query in database native format and a slice of param infos. So the entries in that slice are in the order that they appear in the SQL query. And each entry is of type param info, which has two fields. The first field is the name of the function parameter, and the second is the order that the parameter appears in the function call. And in this way, by walking over the param order, we're able to associate which parameter in the SQL query is associated with which functional parameter. And once we have this information, you can make valid queries to the database. So you pass in that param order slice, and the fixed query to the make executor implementation and make query implementation functions. And then inside of the closure that we're generating using reflect.makefunc, we use that information. And we pass in the param order and the arguments that are supplied at runtime into this build query args function. And the query args that come out, we pass into executor.exec or query.query. And build query args is actually a really simple function. You have an out slice that's all of the database arguments we're building up, and you walk over the param order and use that information in there to pull the right function parameter and put it into the database parameters. And you pass that back in, and you've made a valid database request. So if you go back to the client, we can see programs that use Proteus, and we've got struct tags populated correctly. On our person DAO, we filled in the prop struct tag as well, and the function fields have now been filled in as well. And a call to build and init has been modified to take in a second parameter for Postgres, so we know what database to build for. And in do person stuff, we supply some values so that we can run the code and see that things are working. And we do this, and we run it, and create worked and get worked, but kind of getting back some line noise there, right? We're just printing out what came out of the database, just seeing the pointers on the screen, not terribly useful. But we did talk to the database and get something back for create and get and update and delete. So the next step is to actually handle things coming back. And we'll start with the executors because, quite honestly, they're easy. So when you call exec, you get back a SQL result and an error. SQL result has two methods. One method is supposed to return a created primary key. I've never actually seen it work, so forget about it. The other method returns the number of rows affected by the query, which seems kind of useful, so we'll return that back, as well as an error in case anything went wrong. So given this, we figured out what the return parameter should look like for any of the functions that take in an executor. They'll have a return type of int64 and error, where the int64 is the number of rows that are modified by the query. And the steps, the basic logic is pretty straightforward. After we make the call to executor.exec, we'll look at the SQL result and the error, and if there was an error, we'll handle it and return it back. If there wasn't an error, we're going to get the number of rows affected from the SQL result. If that returned an error, return that error back. And if everything was clean, then we'll return back the number of rows that were affected and nil for the error. And here's what that code looks like. We modified make executor implementation to provide this. We use a reflection package to get the reflected values for the count and error and return that slice of reflect.values. So the zero value for an error never changes across, no matter how many calls you make, it's always exactly the same. So that gets pulled up into a package level private variable. There's no constants in Go or anything that's too complicated, so have to live with it being a variable. We can reuse this over and over again. And if we go back to our client code, we can fill in the return types now for create and update and delete. And we can go back to do person stuff, and we can actually return those values back, and we can print them out to the screen. And get we'll handle in just a little bit. And when you run the code, you can see we get back our create, number of rows 1, no error. Get, still have the line noise, we'll handle that really soon. Update, we make an update to the database, number of rows modified 1. Do a delete from the database, number of rows modified 1. Delete the same thing a second time, number of rows modified 0. So this is working, we're doing the right thing. But to be honest, no one really cares what number of rows returned. What you really want to do is actually get your data out of the database. So let's see how to do that. Most of the time, you want to map the results of a query into a struct and return that back. So let's figure out what the API looks like this time, and then we'll see how to implement it afterwards. So first, we need to define a struct to hold our results. Well, have this person struct with 3 fields, ID, name, and age. And we're going to need to map the fields in the person struct to the columns in the database. And what do we use in Go to map struct fields to incoming values? We use struct tags. And so we need a new struct tag called prof that we use to map the names of the database columns to the fields in our struct. And next, we want to modify our DAOS function get field so that it returns back the proper type. And in this case, it'll be a pointer to person and error. And the reason for using a pointer to person is that if the SQL query returns back no rows, just want to return back nil to indicate nothing came back. So let's look at the make query implementation. Hopefully the code isn't too small for everyone. So first thing we're going to do is set up the values that are constant every time our function's called. Those are a 0 value for the return value that you can return in case of an error or no results, the return type of the function, and a mapper. A mapper is a function that converts a slice of column names and a slice of values into the value that we want to return. And we'll see what build mapper does in just a moment. In our closure, we're going to call this map1row function, which takes in the rows returned from our SQL query, the mapper, and the 0 value, and spits out that result.value. And once we've done that, we can close our rows and return back out. And build mapper function, it does two things. First, it's going to build a map, which has from the column names to the field information, and it does that using that prof field. And this then creates and returns a closure that makes a new instance of the return type, calls a function to populate the instance with the values from the database row, and then returns the result. And here's the function that does the population. And a little bit complicated and all the reflection you have to go through to make all this work, but all it's really doing is looping over all the columns that were passed in, seeing if there was an entry in that map that we built up, and if there is, it tries to assign it to the column, tries to assign it to the field. And if it can be assigned, it works. If it can't be assigned, it returns an error. So finally, we have map1row. It's a function that reads from rows. It makes sure there's data actually in the rows, gets the column names, sets up a slice to hold the results. And after it does that, it copies that row of results into the slice of values. And then it calls mapper to generate that result.value. And that's pretty much it. So one more thing I wanted to point out. Remember that memoization example that I used earlier to demonstrate function generation? Well, we're doing the same thing here. Proteus is using a closure to hold values that we don't want to recalculate over and over again. And in this case, we're getting that mapping between the struct tags and the columns in the database calculated ahead of time. And we're wrapping all this information in a closure that uses the state to populate the struct and turn it into a reflect.value. And we pre-calculate the reflection 0 value as well because it's always the same too. And doing all this pre-calculation helps make Proteus faster. So those are all the changes you need to return a value back from the database. And if we run our code again, now we see get is actually returning back a value. And so we can create, and we call get and get back a value. And when we call update, we will see we update number of rows. And you call get a second time, you get back the updated values. And then you call delete, and it deletes the row from the database. And you call get for a third time, and now nil comes back because there's no more data in the database. But usually you want to return back multiple values, not just a single value. So how are we going to do that? Start with the API again, and then go to implementation. Going to add a new function field to our struct called getAll. Just has a querier, and all it's going to do is return back every row in person, no other parameters for it. Has a return type of a slice of person, and since slices are a reference type, you can return back nil in case no rows came back from our SQL query, and return back the error as well. And we'll add a few extra create calls to our database, so that way we have some data to actually pull back more than one thing. And now for the implementation. What's actually kind of nice is that supporting a slice is not too difficult, a little bit of a help from reflection. So what we're going to do is check the first return type that came back for our function, that was our function field. And we're going to see if it's a slice or not. And if the return type for that function is a slice, we're going to use a function called mapAllRows. And if it's not a slice, we use that map1row we had before. And you can assign a function to a variable. So we have this row mapper variable that holds a reference to map1row by default. And if it's actually a slice, then it changes it to point to a closure that wraps calling mapAllRows. And then in the body of our closure that actually runs our SQL queries, all we do is swap out map1row with row mapper. And now it will call the right function. And if you look at mapAllRows, that's all that's left to do, it's really similar to map1row. We use reflection to make a slice with the reflect.makeSlice function. And instead of just pulling back the first row, we have a for loop that iterates all of the rows in rows and passes them off to mapper and gets back the result and puts it into the slice and returns it back out. So just the same thing we did in map1row, only now it does it for everything, not just for the first value. And when you run this, we have our creates. We create a 1 entry, 2 entries, 3 entries. And we call getAll, and all the results will come back. And you call update, and you call getAll again. And on the next slide, you see the updated result. And when you call delete, and you call getAll again, only 2 results come back because we deleted one of the rows from the database. All right, I think we have time for one more. So far, everything that's been done could have been written fairly easily without using Proteus. We've been pretty boring and repetitive, but not too difficult. So let's try to do something that Proteus makes a lot easier to implement. Let's make in clauses easier. You ever had to write a SQL query with an in clause, you know that it's kind of a pain to deal with in straight SQL, because you need to have one placeholder in the clause for every value that you want to pass in, but you often don't know ahead of time how many values are going to be. So you need to write code that dynamically builds up your SQL query, and doing that leads to the chance for mistakes and SQL injection attacks. So let's see how to automate this. First thing we're going to do is add another function field to our struct, and it's called getByAge. And one of the parameters is a slice of ints called ages. And in our in clause in our SQL query, we just have :ages:, a single placeholder. So let's see what we need to do to figure out the insides. What we need to be able to do is to generate a slightly different query when a slice is passed in as a parameter. If there aren't any slice parameters, the query is going to be constant, and we want to do as little extra work as possible, so we should only generate different query strings at call time when there's a slice, and reuse the same query string when there isn't. Luckily, Go's standard library includes something that should generate strings when you need them, and that would be the templating library. So what we need to do is to turn our incoming query into a Go template. And if there aren't any slices in the query, we can use that template to generate the final query once. And if there are slices in the query, we have to hang on to just enough information to build that query when that function's actually called. And let's see how using templates changes our query generation. So first, we'll look at the case where there are no slices. Start like we did before with the two struct tags, ProQ and ProP. And like before, we make a name order map where the key is the name of the parameter and the value is the position in the function parameter list. And now this is a little bit different. Rather than go straight to generating our SQL query, we instead make a Go template instead. And if you haven't seen Go's templates before, that funny stuff in the braces, that says take the name after the dot and pass it to the function called join that's registered with the template. And the join function is a closure that uses the param adapter to output the right number of query placeholders for that value. And the param order here is a little bit different too. Each entry is still in the order the parameters appear in the query, but the param info now has a third parameter field. It's a Boolean that indicates whether or not that parameter is a slice. In this case, none of them are slices, so we can generate the query immediately. And if we do that, we finalize the query, and we have the same query as before. So let's see what happens when there is a slice. We start with the struct tags, and we generate that name order map, and generate our SQL template and the param order. But this time, there's a slice in param order, so we can't finalize that query ahead of time. So what we do instead is wait for the function to be called. Then we take that SQL template, the param order, and the arguments that were passed in, and we finalize it then. And we see there are two items in the slice, so join generates two values inside of the in clause. And now we have our query. And in order to make this code work, we define an interface called query holder and two implementations. The first one, simple query holder, is just a wrapper around a string, and it returns itself back when it's called with finalize. And this is used when the query can be generated ahead of time. The second one, template query holder, stores the query string, the param adapter, and the param info, so the query can be generated when the function's actually invoked. And this one calls the doFinalize function. Here's doFinalize. I'm not going to go into it. It just sets up the template, executes it, returns back the query string. And we only have to make two changes to our make_executor implementation and make_query implementation functions. The first change is before we passed in query of type string into these functions. Now we pass in a query of type query holder. The other change is adding this one line, query.finalize, where you pass in the arguments that were supplied when the function's invoked, and it spits out the actual finalized query. And build query args has to take a simple change also. Rather than just blindly copying everything into the output arguments for the SQL query, we have to check to see if it's a slice. And if the item is a slice in the param order, then we copy each individual value out of that slice and put that instead into the SQL argument list. And when you run this code, you can see that's all the changes. We set up our DAO, and most of the queries we have, we can finalize those ahead of time. So we go through our templates, and we finalize them immediately. And for create 1, it works. And create 2 and create 3, there's no finalization, same exact behavior as before. So now we're going to call getByAge. And that one, we have to finalize that query at that point, because remember, there was a slice in the parameter list. And calling that generates a query with two placeholders, and we get back two results. And then we have getByAge with a slice that was passed in with 3 values, and it refinalizes the query and puts 3 placeholders into our in clause, and we get back our 3 results. So that's the basic implementation of Proteus. We have a runtime-generated, type-safe, SQL-injection-proof DAO layer that works with the standard Go SQL libraries and adapts to different databases easily. The full Proteus code base has a lot more features, handles a lot more corner cases, has additional validations. Don't have time to cover them all, but you can take a look at the Proteus project on GitHub. The link's at the end of the slides. Read through the documentation, and you can see all the gory details. And that takes us to performance. Implementing all those features with all that reflection, dynamic function generation, I'm sure there's some of you who are thinking, this is going to be slow. After all, even if it's easier to use these techniques to build your DAO layer, it's got to be a lot slower, right? Well, let's find out. I've got a couple of Go benchmark tests. They both run through the exact same SQL queries. One of them is written using Proteus. The other was written using standard Go SQL libraries. The code's all up on GitHub, nothing up my sleeves. It does work. I'm not going to show you the code right now. But I am going to run it right now, and let's see what wins. I actually don't know ahead of time. So here we go. And let's run it and see what wins. I need drum rolls or something to fill the time. All right, we benchmarked Proteus, and all right, around 5 milliseconds to run that. Standard took, and 5.7 milliseconds. So Proteus was faster than doing things with the standard SQL library. Let's try it again. And 5.6 milliseconds for Proteus, and standard is going to take 5. Now this time standard was faster. Still 5 milliseconds versus 5.7 milliseconds. Tiebreaker round. Let's see what actually comes out ahead. All right, guys have the tiebreaker. All right, come on, Proteus. Come on, Proteus. All right, 5.1 milliseconds, and oh, standard won that one. All right, 5.1 versus 5. So it turns out it did not know ahead of time how it was actually going to come out because you run it about, they're about the same, really. Half the time Proteus is going to win, half the time standard is going to win. And the reason why is the cost of talking to the database far outweighs the cost of the reflection. So you're just seeing jitter, talking to the network, whatever's happening on the disk of my local machine. And this is on a database on my local machine. If you're going over a network, the difference is even smaller because the network cost is going to predominate. So one more thing, also, the Proteus version can adapt to any database. The SQL version is written just to work with Postgres. You have to rewrite the SQL queries to make that work with a different database. And while I've used this combination of struct tags and dynamic function generation and reflection and templating to build a SQL solution, it's not limited to just SQL. Adding support for a NoSQL database is pretty straightforward. Just apply a NoSQL adapter that implements the executor and query interfaces, and write a param adapter that specifies what bound parameters look like in your favorite NoSQL database's query language. Proteus takes care of the rest. And what this gets really interesting is that the same techniques can be used for anything that has a DSL. If you're not familiar with the term, a DSL is a domain-specific language. Cut down, usually declarative way to specify how to do something in one particular domain. They're not good for general-purpose programming, but when you have a specific problem, DSLs are often really a good solution for them. And they're not just in programming either. Anyone here play an instrument? Do you read musical notation? Because that's a DSL. I mean, you could probably describe music with words. Say, with your right hand, play G over middle C for one beat, and then play another G, and play an F sharp, or play a B. Or use musical notation. Custom languages are really useful for describing custom problems. And that brings us back to Proteus. SQL is a DSL. It's probably the DSL that we developers encounter most often. And what Proteus is really doing is just translating from a DSL to Go code for one simple set of problems, just talking to a data store. But there are lots of these simple sets of problems out there, and many of them either already have a DSL or they could. So here's one you might have thought of. A REST URL can be thought of as a DSL, and the techniques that I use for Proteus can be used to generate clients for a REST API. I've actually already built a simple one called Sleepy that you can find included with the code samples for this talk. And anytime you can think of a DSL, the Proteus techniques can make your code simpler and allow you to make the boilerplate invisible. So it's really kind of impressive what you can do with Go. Even though it's a language that's famous for having this reduced feature set, it can be used to create declaration-driven code. And by combining the features that Go does have, things like struct tags and function generation and reflection and templating, you can increase the productivity for your team. And you get the same functionality that's available in other languages. And you do all this while still keeping type safety and performance. And most importantly, you're still writing code that feels like Go. And I really think this is just the beginning. Proteus shows that you can build performant, dynamically generated, type-safe, runtime code based on a standard DSL. And we should all go out there and explore new ways to combine these features, and let's see what else we can produce. So thanks for your time.